All right, so the next part of the unit is getting into how do we solve problems with impulse and momentum. So here's a little quick little cheat sheet of how you might want to approach the problem. It's very similar to what we've done in the past. We're sketching the situation, we're setting up a coordinate system and understanding the variables, the knowns, the unknowns. It's essentially the same that we've been doing throughout the year, but of course we're going to put a little twist on it for momentum and just understand it as it's slightly different from how we've solved problems before. So here's a quick example problem that we'll do in class. It gives us that force versus time graph, and again, the area under that curve is the momentum, and the momentum is the mass times the change in velocity. I'm sorry, the impulse, and the impulse is equal to the change in momentum, which is the mass times the change in velocity. So we can use the graphs and information about the change in velocity to figure out the force exerted, and we'll do that one in class. The impulse approximation, it's likely that during an interaction, like a car accident, there's all types of forces and magnitudes, and those are constantly changing. So what we do is we use an approximation, and we ignore all that other stuff, and we just focus on averaging out the forces, but we only think about what's happening before the collision and after the collision. So during the collision, that's really, really complicated. But with momentum, we just care about what happens before and what happens after. And we say whatever's in the between, that we're not even going to worry about that. Okay, so here, got another quick check for you. The cart is going to the left at 2 meters per second and then to the right at 1 meter per second. So really, what is my change in velocity here? Because that's going to get us our change in momentum. And of course, the answer is 3. And you're like, whoa, no, it's 2 to 1. That's how we did kinetic energy. But this is going negative 2 meters per second. And now it's going plus 1 meter per second. So it actually has a total change of 3 meters per second. And 3 meters per second times my 10 kilograms is going to be 30 kilogram meter per second. So you got to be careful with momentum because, again, this is a vector quantity. It has magnitude and direction. Here's a partner problem, of course, that we'll do in class. We have a mass that's going at some velocity, and it's got rocket engines, which thrust a force exerted over time. And we're wondering, what is the final speed? So, like I said, we'll do this in class, but there's some initial momentum. Then there's some impulse exerted on it, and that gets it some final momentum. So we think about a force causes acceleration, and that is true. An impulse causes a change in momentum, and that is also true. So just a couple different ways of thinking about that, and of course, we'll take a look at this during class. So for right now, that's actually all we're going to look at because it all comes down to solving problems in this, and it's just using everything we've talked about before, where we have our formulas of like our impulse is our change in momentum, our momentum is our mass times our velocity. We can have initial momentum, we have final momentum, and our impulse changes that. So that's what we're going to look at in this section.